a U64. Save that. And you can see the ID green has, the ID red has gone away. Anchor discriminator, it looks like we didn't import that. So import create anchor discriminator. Thank you very much. Sorry, offer is not an account of system, is an account of offer. In other words, offer is the struct, and in our we are specifying that the offer account is an instance of that offer struct. So yeah, our whole make offer is complete. There's no red. We now need to work on send offered tokens to vault. So let's make send offered tokens to vault. This is actually a pretty small function. It's going to take a context, which I will spell properly. And so it's going to take a context of make offer, which we will actually borrow because we don't need to write to it. And what else is it going to take? Probably the amount of tokens. So token A offered amount, which is a U64, right? There you go. And we're going to get rid of the logging there. We're just going to say transfer underscore tokens. Oops, tokens. And we will say our options for transfer tokens. So the first thing is context. I think I might need to import this actually. Is it complaining that I need to import this? No, it's just saying that we, because this is going to return a result of nothing. We can't, there either needs to be a semicolon there and we go okay, or we can just remove the okay because transfer tokens returns nothing anyway. So there we go. And it's saying that transfer tokens is not imported. So we need to import it. And it looks a little bit happier now. It's just saying that we need to give it the right arguments, which is what we're going to do. So we're going to borrow context dot accounts. This is going to be our from. It's going to come from maker token account A. And it's going to the vault. So context dot accounts dot vault. How many tokens? Well, that is the token A offered amount. What's next? The mint. Mint will be the context dot accounts, and that will be token mint A. Authority will be the maker, so that's context dot accounts dot maker. And the token program will be whatever the person running the instruction has specified. So context dot accounts dot token underscore program. Save it, and we've filled in all our details that our transfer tokens functions wants. There is no red in the file. We have now created our send offered tokens to vault instruction, and everything in that file looks good. Let's add the final part of make offer, which is that second function called save offer. So pub function save underscore offer. And we'll use the context again. So it's going to be a context of make offer because we want access to all those accounts. So we have our context of make offer. We're going to have an ID, which is that U64. We're going to need to specify how many tokens we want in exchange, which is token B wanted amount. And that will also be a U64, and they are all our options. So this will return a result of nothing. And here is our functions body. I'm just going to turn on word wrap so you can see a little bit easy. There we go. There's a little bit of red there. It's just saying that we haven't returned a result yet, which is true. So we're going to call context.accounts.offer, which is the address of the account that we've calculated based on the seeds. And all we're going to do is just use this set inner method to go and save some stuff into the account at that address. So we provide an offer instance that we're going to make from the ID. The maker in our offer will be from accounts, tokens.accounts.maker and .key, which is their pub key. Token mint A will be context.accounts.token mint A .key. Token mint B will be context.accounts.token mint B .key. How much of token B they want in exchange, which is the token B wanted amount. And also, because this is a PDA, we will be saving the bumps that were used to calculate it, just for performance reasons. Context.bumps.offer. And then, there's a typo there. That context.account should be a context.accounts. And we will also add an OK, because we're going to send this back to the top level instruction handler. That looks good. There is no red in our file. Very happy with that. So we've now finished all the functions we need for makeoffer, as well as the accounts struct that instruction handler is going to need, which specifies all the accounts that we're going to use in this instruction and how we're going to use them. So we're just going to go back into this top-level librs file and make sure that our top-level instruction handler has all the things that we want somebody to provide for this instruction. So obviously, yes, they have a context, which includes all the accounts they're going to use in this instruction, whether they're readable or changeable, or all the other things that we need, whether they need to sign the transaction. But we're also going to need them to specify an ID, which they can come up with themselves. We're going to make it so that people can't reuse IDs anyway. So it's just it's a random number that hasn't been used before. They'll also need to say the amount of token A they want. Token A offered amount, which will be a U64, and also a token B wanted amount, which will be a U64. That looks nice. And then in our make offer body, we need to specify all the things that these two helper functions are using. So instructions, make offer, send offer tokens to vault. You can see from the error that it wants a few things. It wants a context and it wants the token A offered amount. So let's give it the context, which is literally just our context from the parent, and we will borrow that. And we want token A offered amount as well. That looks good. You can see the red has gone away. Save offer also wants to use our context. We can see from the error message, it takes a context, an ID, and a token B wanted amount. So context, ID, and token B wanted amount. Save that. I've got a semicolon on the end of save offer. I don't actually need it because we're going to return whatever save offer returned. So this is just a Rustism. You can omit the semicolon from a line, and that ends up being returned by the function. That looks good. Our program should probably build at this point. We've only done make offer, which is just getting Alice's tokens into the vault and saving details about what she wants. That's good enough a time as any to go and test our program by building it. So let's do a anchor build and build our program. I'll give it a moment to finish. And we can see now that we've updated our program and it builds now, which is great. So we're now officially halfway there. Let's go create takeoffer. So back in our top level librs, we're going to do pub function takeoffer and make a new instruction handler. That is going to take a context, which is a context of takeoffer, which we will create in a moment. And it's going to return a result of nothing. And there's going to be two parts to takeoffer, which you can probably imagine. The first is taking the tokens from the vault and putting those in the taker's account. And the second is taking the tokens from the taker's token B account and sending them straight to the maker's token B account. So let's have a function for each of those. Instructions, take offer. This is going to be a file that we make. And the first function will be called send wanted tokens to maker. And we will pass it the context. And we're going to borrow the context because we don't actually need to write to it. And we're going to say if that fails, that's fine, it can fail. There might be many reasons why it fails. Maybe the person doesn't own the accounts they're trying to use. Yeah, that's fine. If it fails, then it fails. That's Anchor just doing its default checks and saying that something was wrong. And if it fails, that's fine because it's Anchor probably complaining that somebody's trying to take an offer that doesn't exist, or that one of our token accounts isn't actually owned by the taker. So that's all good. Instructions, take offer, and we will have withdraw and close vault. And it will take a context and it will return that. Now we can see there's a little bit of red here. It's just saying that take offer, the accounts struct hasn't been made. That's okay. And the take offer file hasn't been made. So we should probably make our take offer file. So under programs, swap source instructions, new file, take _offer.rs. And let's go create takeoffer.rs. The first thing we're going to need is, well, let's do our import of all the standard Anchor bits. We can probably get most of those from makeoffer. So I'm just going to copy all the imports from makeoffer into takeoffer, and we can remove the ones we don't use. Also in mod.rs, I'm also going to make takeoffer a module and expose it for everyone else. So there we go. So let's create our takeoffer account struct. So it's a pub struct called takeoffer, and it takes an account info item to set the lifetimes of various objects inside it. Also, because it's going to be an Anchor accounts struct, we need to say hash derive accounts, and I need to spell derive correctly. There we go. That looks a little bit better. And it's a capital A for accounts as well. All right. So we have a taker, which is the person who's going to sign this transaction. That's a signer whose lifetime is info. And we'll also say, because the taker is going to not only sign this transaction, but pay for the accounts to be created. So we'll say account mute, so that this we can mutate, or in other words, change the balance of this account so that they can pay for the transaction. We'll have the maker that they need to specify, pub maker, which is a system account. We'll go for the lifetime of info. And that is also mutable because they will have some of their balances changed. We'll have token mint A. And that's an interface account of info and system. Oops, not system, mint. It's a mint account. So it's interface account wrapping around mint. That just means that, again, we can use this on the older token program or the newer token extensions program. We're going to specify there's token mint A and token mint B as well. So let's specify both of those. Token mint A and token mint B. They look good. What else will we need? Well, we'll need the taker's token account A, because that's where we're going to put the tokens that we get from the vault. So pub taker token account A, and that is a box of interface account that lives for info and wraps around token account. And we'll also have the taker token account B, which is where we're going to take tokens from and send them straight to the maker's token account B. So I'll just do a quick little copy paste. I'll add that missing comma. That looks pretty good. What's complaining about there? Just got to make sure that those are all lined up. That wraps around. Yeah, it's gone away. Excellent. Just needed to add another comma. We're going to add some anchor constraints on token account A and B. We'll say, so account, and for taker or token account A, we will say init if needed. Why init if needed? Because the taker may not have any balance of token account A. So if they've never had token A previously, when we move the tokens from the vault into the taker's token account A, we'll need to make a token account A for them. So let's do that, init if needed. And we'll also say we want to specify the mint of this should be the token mint A. So that is, also say who's going to create this this account, by the way. So payer equals taker. So I'm going to pay to make their own token A account. Init if needed. Payer is taker. Associated token mint of this account should be token mint A. And associated token authority, which is kind of the, if you think of owners in Solana are like program owners, but authority is like the account level owner. So that authority is taker. And the token program should just be the token program that we specified. So that is associated token program should be token program. Cool. So taker token account A is a box of interface account of token account. That looks good. Init if needed. Payer is taker. And the mint should be token mint A. The authority should be the taker, and the token program should be the token program specified in the instruction. A little bit of red there. What's it complaining about? A non-optional init constraint requires a non-optional system program field to exist in the account validation structure. That's okay. I haven't specified the system program yet. So once I add the system program yet, that error will go away. So we've got the taker token account B. And let's add some constraints here. Account. And for this will be mutable because its balance will change. And all we need to do is copy some of our constraints from earlier, but this is taker token account B, so we need to make sure that we're checking that it is the token mint B, not token mint A. That looks good. There's another account that will, another token account we'll be mentioning here. which is when we will take tokens from the taker's token account B, and we'll send them to the maker's token account B. So pub maker token account B, and let's add some constraints. So Anchor can check all these good things for us. The maker's token account B will also be init if needed, because the maker, again, may not have ever had any of these tokens before. So init if needed. Payer to create this account will be the taker. And the mint authority and token program, I'm going to copy and just double check. So the mint for the maker token account B should be token mint B. That's good. The authority is not the taker, it will be the maker, because this is the maker's token account. This is Alice, this is not Bob. We need to make sure that Alice owns Alice's account that holds token B. And the token program is the token program they specified in the instruction. That is all good. Finally, oh yes, we're going to involve the offer account. So the offer is just an account who will live for the lifetime of info, and it's of the type offer. And what do we need to add to this? Well, let's start our little Anchor account constraints. This will be mutable. Why? Because we're going to close this offer account when the offer is taken. We'll also, when we close this account, we will also return the sol in it back to the maker. Why? Because the maker made the offer account in the first place. So it seems fair that when we close this account, we should refund that back to the maker. Close equals maker. And we're going to just do some little, we're going to specify some things we want to exist inside the struct. So has1 equals maker, has1 equals token mint A, has1 equals token mint B, and the seeds for this are exactly the same as what they were before, which is the bytes of the word offer and the maker's key as _ref and the offer ID. Offer.id.to little endian bytes. So we have it as bytes as ref. There we go. That looks good. And finally, the bump equals offer.bump. Always save your bumps. That looks good. Excellent. What else do we need? We need the vault, because obviously this take offer is going to move tokens from the vault. And yes, you can probably already imagine that the vault will be mutable. So let's go set that up. The vault is an interface account. Lives the lifetime of info, and it is wrapping around just a regular old token account. Again, if we weren't doing this compatibility between the older token program and token extensions program, Vault would just be token account, but because we want this compatibility layer, the best practice is to use these interface accounts everywhere. So we have our account, and the vault is obviously going to be mutable because we're going to take all the tokens out and we're going to give them to the taker. And the rest is just making sure that the mint of the token account is exactly what we expect. So I'm going to copy these, but I'm also going to check them. So the mint of the vault will be token mint A, because we took tokens from the maker's token account A and we put them in the vault, and they will be of the mint A. The authority of the vault account will neither be the maker or the taker. The vault account is actually, its authority is the offer account. This means that the vault is controlled by the offer. It's not controlled by the maker or the taker. It's controlled by the offer, which is the offer account can actually sign for things. And when we send tokens from the vault, they will be signed for by the offer's own account. And our token program will be our token program. That looks good. Save that. And finally, we've got the normal checks about all our programs. I'm just going to copy those from make offer. System program, and associated token program. Thank you very much. I will paste those in. And that looks good. No errors, no warnings. Just a couple of unused imports. That's okay. I'll delete them once I've finished writing this file. So we've made our takeoffer struct, which is going to specify all the accounts that we need to check as part of an incoming takeoffer instruction. And we've created the top-level instruction handler in librs, which we called takeoffer. And back in librs, we said we wanted to have two functions. One was called send wanted tokens to maker, and the other was withdraw and close vaults. So in takeoffer.rs, let's create the first of those two functions. So to make that send wanted tokens to maker function, we'll do pub function send wanted tokens to maker. And that's going to take a context, which is a context of make offer. And we're going to borrow that item as well. Also, that's going to return a result of nothing. And let's make that happen. So this is actually just going to be very simple. To send the wanted tokens to the maker, I send the tokens from taker's token B account straight to the maker's token B account. It's just going to be transfer tokens, our little helper function we made earlier. And the from will be, we'll borrow this, context dot accounts taker token account B. The to will go to the maker's token account B. Context dot accounts dot maker token account B. The amount of token B to send will come from the offer. So that's context dot accounts dot offer dot token B wanted amount. The mint will be and context dot accounts token mint B. The authority, i.e. the person who controls that account, will be the taker. And the token program will be context.accounts.token program, token underscore program. That looks good. And this is a context of take offer. I did notice that my autocomplete was a little bit funny there, so that explains it. I think I said I wrote make offer when I should have written take offer. So there you go. So yeah, that actually looks good. So we're transferring tokens from the taker's token account B straight to the maker's token account B. We're transferring the exact amount that the maker wanted. We're making sure the mint of the accounts are token mint B. We're checking that the authority of the from account is the taker, because this transfer is going straight from the taker to the maker. And we're just making sure the token program is the same one that we specified in the instructions. That looks good. So we've just completed our send wanted tokens to maker function. The final part for take offer is to complete the other helper function we made, which is called withdraw and close vault. So let's make that now. Pub function withdraw and close vault. And it's going to return a result of nothing. The options it will take are just simply the context again. Context. And that's the context of take offer. Now, we're going to do a transfer here, but it's not going to be a transfer from a regular account. Instead, we're actually going to transfer from our Vault account, which is owned by our offer account. So this is a PDA transfer. It's a transfer that's being signed for by our offer account itself. So we're not going to reuse our helper function, which is focused on a different type of transfer. We're going to make our own calls to transfer checked with a slightly different set of options this time. So we make the seeds. Which we will borrow. And the first of the seeds will be the bytes for the text offer. You might remember this. This is the seeds we used to get the address of the offer account. So we're going to use that to actually sign this transaction. The second option, the second seed for that account will be context.accounts.maker to account info .key.asRef. What else will we need? The offer ID, context.accounts.offer.id.to little Indian bytes. I'll do a little bit of magic on it there. And then finally, bump, which we'll borrow, context.accounts.offer.bump. We'll also want to borrow that offer ID. So let's, that looks good. Little semicolon. We can actually have multiple signers when we do a transfer from a PDA like this, but we only have one in this case. So we're going to wrap our seeds into a bigger signer seeds array. Let signer underscore seeds equals bigger array and just our seeds. Do a little magic there. Looks good. We're going to make the accounts that are going to be involved in our transfer checked function. So that is let accounts equals transfer checked. This is really the options for our transfer checked. From context.accounts.vault.to account info, comma, mint. Actually, let's do the to first. I think it's a little bit more. Context.accounts.to is the taker. These will go to the taker's token account A because we're going to take the accounts from the vault and put them into the taker's token account A because the tokens in the vault are of the type token A. Taker's token account A, oh yes, to account info, comma, the mint, which is context.accounts.taker token mint A, remain obviously to account info, and our authority, which will be our offer account. Context.accounts.offer.to account info. Final comment there, and doesn't like transfer checked. It's okay, we just need to import it. Import transfer checked from token 22 or token interface. I'm pretty sure I want the one from token interface. That'll allow us to use both older and new token programs, but let me double check. Yeah, that looks a little bit better. There's actually a transfer checked right below token interface, so make sure you import that one, and not the really long one that I imported. That is happier now. Excellent. So we've got our accounts all set up for this token transfer we're about to do. We're going to make a little CPI context. Let CPI context equals CPI context new with signer. And all we're really doing here is combining the accounts, which are effectively the options for transfer checked, the token program, and the signer seeds, which allow us to sign for this transaction as the offer. So the program will be context.accounts.token program to account info. I might actually, like the next time I get some time free, I might make a little wrapper for this because I'm getting tired of typing to account info. Maybe you are too. And accounts and signer seeds. That looks good. Oh, we just want to borrow that and it will be happy. Yep, that looks good. No red. The only red there is our result. That's fine. We haven't actually written the code for the result yet. What's next? We've got our CPI context, and let's actually do the transfer now. So that's transfer checked. And takes a context, which is our CPI context. It takes the amount that we're going to transfer. So that's we're going to get that from the vault. So context dot accounts dot accounts dot vault dot amount. There we go. And the decimals. Context dot accounts mint token A dot decimals. Token mint A decimals. That's complaining. It wants me probably to import it. Cannot find function in that scope. That's fine. Import transfer checked. And we probably want to import it straight from token interface. So not token 22 and not token. I think there's I think we can just import it straight from token interface manually. Let's do that. Comma transfer checked. And there. That looks good. There's a little bit of red elsewhere. What's this? Check that out in a moment. Oh, I think. Oh yeah, that's just it saying that we need to do our return, which is fine. We've done our transfer checked, which is taken that's the withdrawal part of withdraw and close vault. That has moved the token A tokens from the vault into the taker's token A account. Great. If you're wondering why we need to provide the decimals for transfer checked, it's part of the checked part of transfer checked. It includes some safety checks like making sure that you explicitly provide the decimals. So we've moved our tokens from the vault into the taker's token A account. The other part of this is to close down the vault itself so it can't be reused. So we're going to make a close account struct, which is going to be the options that we provide to another CPI to the close account function. So let's do that now. Let accounts, and it will equals close account. We have three options: the account, which will be the vault itself, context.accounts.vault, and to account info. We'll have our destination, which is where we're going to refund any LAMP ports that were in that account. We'll send them to the taker, but we could send them to the maker as well. Context.accounts.taker.toAccountInfo. and the authority, which is who's allowed to, who's doing this, which is the offer. The offer account owns the vault. That's context.accounts.offer, and you guessed it, to account info. That looks good. I needed to import close account, by the way, as well. I've done that right at the top here, and it comes directly from token interface. So make sure that you import things from token interface, not from the old token program specifically, not from token 22 specifically. Import from token interface. Great, so here's our accounts. Let's make a CPI context so that we can go and invoke our close account function. That's a CPI context and new with signer. The program will be context.accounts.token program and to account info. The accounts we've actually already specified above, and signer seeds. I think we just need to borrow that and it should be okay. Yep, that looks fine. And then, so we have our CPI context, everything we need to go and invoke close account. Let's actually invoke a close account. Close account. And yeah, CPI context. Oops. What's it saying there? Mismatch types. Ooh, I can see what I'm doing there. I am not using the right version of close account. So let's just go back to my imports and double check that. Yeah, I've got token close account. I want token interface close account. It's one thing to be really careful of when you're using an editor that suggests imports. Do make sure you're importing everything from token interface, not from the token program. And you'll see that that's now fixed. Great, and I actually can omit the semicolon because we're going to return whatever closed account returns from this function. That looks good. So we've created our make offer, we've created our take offer, the high-level instruction handlers and all the helper functions and the structs of accounts they need. Let's go and review librs. We've got our take offer, withdraw, and close vault. That all looks good. We should probably check that our program compiles. So back over here in our terminal, let's do a anchor build. A couple of unused imports, that's okay. I might actually get rid of those just for the sake of cleanliness. We weren't using anchor discriminator. Ooh, we need to handle any errors in transfer checked. So what we can do with that is we can say a little question mark there, and that says, look, if transfer checked throws an error, throw an error. That's, that's okay. We can deal with that. That looks a little bit better. So back in our compiler, let's clear the screen, anchor build again. And that builds. We now have a working swap program where someone can offer their tokens to be taken, and then someone can take that offer and receive those tokens directly in their own accounts. So we've run our program and it builds. Next step is to test it. We've already got some tests we've prepared for you, but I'll go through them here. This is swap.ts under the test directory, and it's pretty simple. We import a few common bits and pieces, anchor itself, the chai assertion library, the Solana helpers, make a few variables, and we have one block of tests called swap. That connects to Anchor, which allows Anchor to use the keys and the networks set up in our anchor.toml. And we set up some variables we're going to use in a moment for Alice, Bob, token mint A, and token mint B. Our before handler is really simple. It just creates some users, some mints, and some token accounts, and uses those mints to mint a particular balance of tokens, so that Alice has a lot of token A and that Bob has a lot of token B. There's two tests. and the first is our make token test. Make sure that it puts the tokens Alice offers into the vault when Alice makes an offer. So we're simply going to get our list of accounts together, and then send that transaction off. Program methods.makeOffer with our options, the accounts we want, and our signer is Alice. Afterwards, we're going to check the balance of the vault, and we're going to check the offer account has the data that we expect. The second test is pretty simple. It's program methods.takeOffer, confirms the transaction, and checks Bob's accounts after running the test. Also, we could add a test to make sure that the vault is closed. I don't think we are here, but I can add one in a moment. You'll also note I run .slow, and then I have a variable set to, I think it's 60 seconds. Because Anchor tests connect to our local validator, by default, Anchor shows them as slow because Mocha actually shows them as slow because they take anything that takes more than, I think, half of 30 seconds is shown as slow. So if I set my slow threshold to 60 seconds, anything that takes half of 60 seconds will be shown as slow. Our tests only take 15 seconds, so they won't be shown as slow. You didn't really have to worry about that too much. It's just a me thing. I hate my tests being shown as slow. I like to establish a bit of a baseline for how long a test should take. So yeah, pretty simple. We just have one describe block and a test that goes and checks make offer and another test that checks take offer. If we run those, and you can import them into your own program, you can get them from the link that we will add to this presentation. You can actually call your take offer and make offer and check that they work as expected. Give it a sec. As I said, these tests take about, I don't know, maybe 15, 16 seconds each. And then we can see the first test is finished, which is puts the tokens Alice offers into the vault when Alice makes an offer. And in a moment, our second test should hopefully finish as well. There we go. Puts the tokens from the vault into Bob's accounts and gives Alice Bob's tokens when Bob takes the offer. So this program is a great example of the benefits of DeFi. Alice had some of one token and wanted another token. She didn't know Bob. Bob, at some point in the future, came along, took that offer that Alice made, exchanged his tokens for Alice's tokens, and each side got 100% of what the other person was offering without anyone in between taking a portion of anything. Also, the other useful thing about this program is that it shows you how to handle tokens in your own program, to how to hold tokens, and how to sign to transfer those tokens out of places where they're stored using CPIs. So I'll see you in the next lesson.
Imagine a company that wants to reward its employees with tokens, ensuring they remain motivated and committed to the project. This process is known as token vesting. Token vesting is a mechanism used by cryptocurrency projects to distribute tokens over time to certain stakeholders, like employees, advisors, or investors. Instead of granting all the tokens immediately, vesting restricts access to the tokens over a set schedule. This aligns incentives and prevents stakeholders from selling all their holdings at once, potentially destabilizing the token's value. In the upcoming tutorial, we'll write our own vesting contract. Our contract will have the following user experience. A company will be able to come to the DApp to initialize their own vesting contract and specify the mint address and total supply of the locked tokens. Next, the company will be able to add employees with their individual vesting details, which includes the total amount of tokens allocated to the employee, the vesting duration, and the cliff. The cliff is the initial period where no tokens at all can be claimed. Say the cliff is 6 months. Then for the first 6 months, the employee will have 0 unlocked tokens. After the cliff expires, unlocking begins according to the monthly schedule. Employees can also use this DApp to view the status of their vested tokens and claim any unlocked tokens. This project enables transparent, automated vesting on Solana. Companies can set customized vesting schedules for any SPL tokens, and employees can clearly track their vesting progress. So in summary, token vesting aligns incentives for projects distributing tokens over time. Our smart contract brings secure on-chain token vesting to Solana. By the end of this tutorial, we'll accomplish writing the smart contract code, running tests, creating a front end, and connecting the smart contract to the front end, creating a fully functioning decentralized application. Let's get started. All right, so let's create the vesting DApp. We're going to be using the npx create Solana DApp scaffold because it connects both a front end and a back end in one workspace and makes it a lot easier when you're making a full decentralized application. So let's get started by setting up the scaffold. We're going to navigate to our terminal and just type in npx create Solana DApp. And now we're going to enter the project name. We'll do token vesting. We'll select the preset for Next.js, Tailwind, and then the Anchor counter program. And this is creating a new workspace with npm. So it's going to take a second to load. We'll wait for everything to generate, and then we're going to open this workspace in VS Code and get started. Okay, so this creates a new folder inside the directory that you ran the command. So we're just going to cd into that folder. And then we're going to open in VS Code. Okay. And just to get everyone familiar with this scaffold, how it sets up the workspace for you, you have your web folder that has everything for the front end of the application. And you can see the app, the components, and all of the needed configurations. We're going to work with this later. So we're going to start out with our Anchor smart contract. So in the Anchor folder, you can see it has everything set up for the back end of the application. We have our programs, and then you go into source, and this is where the main smart contract lives in your librs. Now, we also have a few other folders generated that we're going to use later on in this application. But let's just first start with our librs. So you can see this is just a basic counter that was generated. If you actually run this with npm run dev, it's going to actually show the front end and a working counter. But we're going to change all of this for our vesting contract. So what we can do is just delete everything within the program. As you now know, by working through the bootcamp, this program macro defines all of the instructions for your smart contracts, and then you have the corresponding data structures for all of your context. So we're just going to delete everything related to the counter and just have the basic setup for an Anchor smart contract. So that's using the Anchor lang import. It has your declare ID with your program ID of the smart contract. And then this is where all of your instructions are going to live. Now, what we need to do is rename everything from counter over to vesting. So let's start by updating the name of this program to vesting. And then we're going to navigate into our cargo file. So the package name is counter still, so we'll update this to vesting. Okay. And then let's see, we're just going to Command-Shift-F and see everywhere else that counter is written. And we just want to update that. So it's going to be in quite a few places. This will take just a second. Anything related to the TypeScript files for our web app, we're just going to deal with later when we start working on the front end. So all of this we can just ignore for now. So now we have to set up our cargo TOML for this program. And in our vesting contract, we're going to be moving SPL tokens around, as well as using a Solana program. So we're going to update our dependencies in our cargo TOML to use both of those crates. So we can just open up our terminal and run cargo add. And we're going to add first our Anchor SPL. Sorry, we actually need to navigate into our Anchor directory. So one thing to note whenever you're using the Create Solana DApp scaffold is everything related to the Anchor smart contract lives in the Anchor folder. So whenever you're running Anchor commands or any of your cargo commands, it has to be done in the Anchor folder. So we'll cd into Anchor, and now we can run cargo add Anchor SPL. Okay, so you can see our dependency updated with Anchor SPL. And now if you're following along, depending on the time that you're following along, this might have a different version. So if you want to make sure that everything stays consistent with the rest of this tutorial and make sure all the dependencies are compatible, I would recommend using the dependency versions that we have here in our cargo toml. So now we'll also add in the Solana program. So we'll do cargo add Solana program. And if you want to specify a specific version, we'll just do that at for the version that we want. So we're going to use 1.18.17. Okay, and now our Solana program is updated. And now another thing that we're going to need in our dependencies is the init if needed feature for anchor link. So I'll explain what this does later on when we're actually using it, but for now, let's just get our cargo set up. We're going to do cargo add anchor link and add the feature flag. And this will just be init if needed. Okay, and you can see that the dependency was updated with the feature init if needed. And one last thing to update in our cargo toml is our IDL build feature. So because we're using the Anchor SPL crate, we also need to update our IDL build to work with Anchor SPL. So in our IDL build, we'll just add Anchor SPL dash IDL build. Now our cargo is up to date and we can navigate back to our librs. So let's think about what we're building here. We're doing a vesting contract. And as we explained in the introduction, is we have two perspectives. We have our employee perspective and our employer perspective. So first, we're going to think about the employer. We're going to be creating a vesting contract, so we have to initialize that. And then we also have to add in the ability for the employer to add employees. And then lastly, we need to allow for the employees to be able to claim their tokens once they have vested. So let's start with initializing a vesting contract. So we can first define the instruction within our program macro, and we'll just do pub-fn, and we'll name it create vesting account. Whenever you're defining an instruction, you always have the first parameter is going to be your context. So we're going to just define the context, and then we're also going to want to create a custom data structure for this context. So we'll name that data structure create vesting account. And it will return a result. And then we'll write the logic for our instruction, but first we need to define what this data structure is. So outside of our program macro, we can go down here and we'll use derive accounts, and we're going to just define the struct. So pub struct, and this will be create vesting account. And we need to make sure we use the lifetime specifier. So what this context is doing is it is passing through all of the accounts that are needed to process the instruction that you're writing. So let's explain all the accounts that we need. First, we need the signer. So we'll write an account, and we need that to be mutable because the signer is going to be paying rent. So their account state is going to be changing when their balance of SOL changes. So we'll name them signer, and then the type is going to be a signer with the lifetime specifier. Okay. So one thing to note when we're writing all of our accounts is that with Anchor, each account used in a transaction, it's declared in a context structure with specific traits. And these traits dictate how the account can be accessed, like mutability, which is why we needed to specify the mutability for the signer because their account state is going to be changing. And in Rust, as you know, all variables are immutable by default. So here, when we define our account macro, we're going to have to specify all the constraints for the next account that we're writing. And we're going to be defining our vesting account, which is what we're creating with the instruction. So because we're creating the vesting account, we want to use the init constraint to specify that we're initializing an account when we're writing the instruction. So let's use our account macro. And then inside, we're going to first specify init.
Now, whenever you're initializing an account, it's going to be taking up space on chain, and that space you need to pay for in rent. So we need to be able to calculate the space. So we can just define the space constraint, and we'll do the anchor discriminant